Right. Okay, so now let's continue discussing Monte Carlo methods. So that's our last portion of the lecture on um, Monte Carlo methods. So today I'm going to start with a review of what we discussed in the last lecture with an example. The example is on how to mine an asteroid. All right, so this is basically an imaginary scenario where we want to mine this asteroid. And we have a spacecraft. Let's say we have a miner over here and with a rocket. So that we are approaching the asteroid with a velocity of 250 meters per second. All right. So basically, what we want to do is we want to slow down the miner spacecraft to a velocity of 0 before we collide with the asteroid, so that we can start mining it. All right. So so let's imagine this spacecraft has two thrusters. One is a solid rocket booster, and the thing is, once you turn it on, you cannot stop it. It'll burn and finish burning, and then you have a let's say a gas thruster that has very little thrust, but like you are going to be able to do a more fine control. So let's imagine our gas thruster can produce an acceleration of just let's say 0.01 meters per second square. That's very small, but like it's useful for fine tuning the location and velocity of the miner. And what I'm going to be making probabilistic is the behavior of the solid rocket booster. So the solid rocket booster has a stochastic behavior, because not every solid rocket booster you're going to build is going to be exactly the same. They are going to be producing a different delta V for each one you put on in a different spacecraft, and they will have slightly different burn time. So let's exaggerate a little bit and put a PDF of both the delta V and the burn time, right? So let's say this is the burn time T, and the delta V satisfies a triangular distribution. So the PDF of the delta V is triangular with a minimum of, let's say, 210 meters per second. So let's say the unit is meters per second. We're approaching with 250 meters per second. And the maximum is going to be exactly 250. So if you if you get the maximum delta V, you won't have to decelerate at all. Okay, and the peak is at 220 meters per second. Now that's the PDF of the delta V. How about the PDF of the burn time? So that's how long it takes for the solid rocket booster to produce that delta V. And for now, let's assume the deceleration from the solid rocket booster is uniform, so that with the delta V and T, you can know exactly the trajectory. Okay, and imagine we have an exponential distribution of the burn time. The burn time would never be less than 55 seconds. So let's see, this is seconds. And it has a exponential distribution, right? And with the lambda of the exponential distribution being, let's say, 5 seconds. So that means the PDF of t, right, as a function of a small t. So this big T is a random variable. The small t, the PDF at small t, illustrates what is the probability density of this time at the small t. It is going to be equal to an exponential function of minus lambda. Oh, actually, lambda is actually, it has to be a rate, 1/5 seconds, right? So minus lambda times t minus 55. And in order for this thing to integrate to 1, the exponential function has to be multiplied by lambda. And the triangular distribution PDF of delta V, let's say small v, is equal to, it depends on whether the small v is in which range. It is either equal to 0 if v is less than 210, or it's going to be a linear function that goes from 0 to maximum. And what is the maximum here? Let's see, the base of the triangle is 40. And in order for the triangle to integrate to 1 with the area of 1, right, the height has to be 1 divided by 20, right, or 0.05. Okay, so the PDF is going to be v minus 120 times 20 if v is in the interval of 120 and 210 and 220. All right. Oh, times actually 2, not 20, because that's 2 is going to be the slope of this, right? So over a range of sorry for that. So over a range of 10, the PDF has raised for 1/20. So yeah, it's divided by that means the slope is 1/20 divided by 10, which is 1/200. So this divided by 200 is going to be the function within this region, right? Now the third region is from 220 to 250. And the slope over this region is 1/20 divided by 30, and it's negative. So in this region, the function is going to be 250 minus v divided by 600, right? That is going to be the PDF function in the third region. And of course, when v is greater than 250, the PDF is going to be 0. Okay, so this is a complete description of the problem. So we want to approach an asteroid starting with a velocity of 250 meters per second. We have a probabilistically behaving solid rocket booster that decelerates us. And the problem is, how far away should I begin decelerating, right? So that the probability I'm going to crash into the asteroid is low enough. In order to answer this question, we need to be able to calculate such a probability, assuming we start decelerating at a certain location, right? So let's look at how do we analyze this problem. Okay, and so let's say this is our. We want to look at our velocity versus time plot. And with the velocity versus time plot, we have a distance versus time plot. So the velocity versus time plot is going to be decelerating. So we have two intervals. One interval is from 0 to t, which is going to be probabilistic, right? And over this region, we are going to be achieving a delta v of also being probabilistic nature. And after that, we are going to be activating our gas thruster. So we will further decelerate because with almost a 1 probability, the solid rocket booster is not going to achieve the desired deceleration of 250 meters per second. So we'll continue a much slower deceleration, right, until we reach a velocity of 0. And the goal is that over this region, the whole distance covered, which is going to be an integral of the velocity curve, right? It's sufficient. The distance I start with over here, because as the velocity decreases, we'll decrease the distance, and then finally I want the distance to be small but not 0 until I reach a velocity of 0. So now the question is, how can I calculate the probability that I'm going to crash into the asteroid, assuming I start at a distance of, let's say, x when I start the solid rocket booster. All right. So we haven't done this for a long time, but like I would actually put you into pairs of rooms, and I would let you discuss with each other how do you solve this problem. All right, questions? The question is, if I start with a distance of x, how do I calculate the probability I'm going to crash into the asteroid? Any questions before I put you into rooms? Yes? No? Okay. Yeah, I mean, even when you're in rooms, you can ask questions by raising your hand. So let's see.